Hillel Wust-Bloch, and he's an expert on earthquakes, and he's going to tell us about earthquakes in the region, or monitoring them.
Good. Okay, I'll try to speak loud. I think it will avoid you the technical. Okay, sorry. Okay, good morning, everybody. Thank you, Tzvi, for this. I could not have dreamed of a better introduction. I'm going to take, if it's not too early in the morning, I'm going to take you earthquake fishing in the Dead Sea. So beyond a nod to the book by Paul Torke entitled Salmon Fishing in Yemen, which are suggested by my children, it's actually a good metaphor to explain the type of activities seismologists can do in the Dead Sea, and as well as people fish either for pleasure or for subsistence, seismologists do fundamental research and also try to save lives. So I will try to touch on both of these things. And now I'd like to go to the Dead Sea, and actually the big issue we have in the Dead Sea, our mission, or one of our missions in seismology, is to try to assess the seismic hazard. And to do that, we need to characterize a system. And as scientists, we need data, big data. Now, the big problem is that although Tzvi told you or convinced you that it's a marvelous area, for seismologists, it's not that great. So, and this is one of the lessons. It will really push us to the extreme. So we have some kind of an ambiguous situation in the Dead Sea. When you look at the history, we have an amazing record, massive destruction. When you measure it, for instance, with GPS, you have plate displacement on both sides of the plate boundary. It's only 5 millimeters a year. So if you look across, Jordan goes north 5 millimeters per year. It's not much. It's less than your fingernails. So, and it also means that the seismicity rate is much lower. For instance, it's 10 times, an order of magnitude less than California. So again, we don't have a lot of data, and it's bad because there is no way to assess properly a system if you have little data. So we have to now find and develop techniques to lower the threshold of detection to get more events. Okay? The second challenge we have, Tzvi touched upon it, is that we have, in between this plate boundary, we have an extremely deep trough of sediments. I pass you all the details that you saw. It's complex, and actually we don't know much about it. And it's also bad for us, because it doesn't help us to locate the things. It filters everything. And you can see even, like, if you look at archaeological sites, on the little diagram there at the bottom, yeah, here, you can see that the red dots are archaeological sites that were systematically destroyed by earthquakes. So you can see that that beautiful trough of sediments, which is useful for environmental studies, for us is a huge problem. It filters and creates massive headaches. And to make things worse, when you look at the surface, there are two seismic networks, one on Israel side, one on the Jordan side. Thank God the Israeli one is presently being completely upgraded, but the networks are substandard. We have very poor catalogs. We have, again, very few events and data. And we have a situation, actually, and both of them don't correspond transfer data, especially not in real time, which we need. So we have a situation which people encounter a lot, seismologists encounter a lot in the world, is that we have a seismic network, but the source we're trying to observe is out of the network. And so Israelis look at the Dead Sea fault, we see only one side, or we're only on one side, and the Jordanians also. And that's the last challenge. So now I'd like to go for a very basic refresher of seismology. The vast majority of seismic networks look like this. It's basically a network of single individual sensors connected and connected to one server, which does the analysis. And we're identifying different phases, computing travel time, and if we know the velocity model, we can locate the events, because that's one of the parameters. We need to know where the earthquake occurred. And then we'll try to assess its magnitude. Now, this approach is standard, is robust. It has a few problems for us. First of all, if you want to detect very weak events, you need a very dense network, and it's expensive and it's complicated. The next thing that's a little complicated is that you need a good velocity model. You need to know what's under the system, otherwise your locations will be erroneous. And the last thing is that when you work in real time, for instance, I will show you applications for early warning systems, to locate an event, you need at least, here it's 3 because it's in 2 dimensions, but you need at least 4 arrivals. You need the event to be detected at least for 4 stations, often a lot more before you can provide an alert. And time, I will show you in a few seconds, time is the essence for early warning systems. So it's a little bit the weak point of this system. So for a long time, we scratched our heads and we tried to figure out how we can really characterize this seismicity, these events we don't see here. They're rare, they're not many, so we cannot miss them. So we came up with the idea of actually setting up, instead of a network of interval stations, setting up what we call mini array or small aperture arrays. It's a technique that's used in a lot of other fields, in astronomy, for instance. So what we do is that in the surface of about a few football stadium, we spread 6 to 12 sensors. We connect them to one single data logger, so we have a unique timestamp. And what it does is that it gives us, we look afterwards at the waveforms, we cross-correlate them in time, and it allows us to get 2 parameters which are very important, which other system cannot really get. One is a slowness, which is actually the velocity of the wavefront that crosses the array. And the second one is the back azimuth. It's basically the direction in which the wavefront goes or comes to. So basically it points to the smoking gun or the source of the earthquake. So when you look at here below, what we've done is that what we've done is to deploy a series of mini arrays instead of just standard networks. And the big advantage in that is time. You need, with 1 or possibly 2 mini arrays, you already have all the parameters you need to lock onto the source. Now I'd like to show you what we've actually done here. With the red triangles are stations that we have that are running. The green triangle is where we're sitting today. We actually are deploying it. We have one working here. And the other ones are mainly are here. And as Tzvi mentioned before, it's a transborder venture. We're working with Palestinian and Jordan colleagues. So we also have sensors on the other side of the fault. There are not many networks that are transborder or shared by countries. I was told yesterday by our Japanese colleague that actually in Japan and Taiwan and I think South Korea, they also share data in real time. We do too, and in not easy conditions. And the latency is in the order of 20 milliseconds, so we're extremely fast. I will not go into the other details which are technical, but maybe one of the main issues is that although if you look outside here, it's look pastoral, desertic, and you don't see many people. You see more ibexes maybe than people. A little north of it, where we are here, and this is mainly why we've put our cluster of mini arrays there, within a radius of 20 kilometers from the fault line, you have about 80 million people. Okay, so it's not exactly Los Angeles, but you have a lot of people very near the fault. And this is why that was one of the main motivation, first to be able to work with our colleagues, but also to try to understand better the seismicity and monitor it in real time there, closest to the big population centers. Now, I think I will pass on to the fundamental research we do. We do a lot of standard things. We also do calibration of the mini arrays and everything. I think after what I heard yesterday, I felt a little guilty that we tend to do maybe too much really hard science, and we forget that there are people living around us. So I'd like to show you an application actually on early warning systems. And what I will show you now is this algorithm that we've developed. So what you see here is two of our mini arrays. One is in Ovnat, one is in Allenby on a border crossing. This Jerusalem Amman is here, and this will be the earthquake. Okay, what you will see, it will happen very fast because it's in real time. I mean, it's a replay, but it's in real time. So basically, our mini arrays work as a guard. It just senses everything, every transient that goes through, and analyzes it. So, and we have the possibility, because we know the slowness, you have the possibility of discriminating between an earthquake, which moves very fast, about 5 kilometers a second, and sound or other noise, okay? So you have this guard, it scans around, and you will see the back azimuth, the beam going in different directions. When it's green, it's sound velocity, it's not interesting for us. And as soon as it's seismic, it locks on it and it's red. So you will see, first it will come from here, it will reach the station, from the source it propagates radially, hits Allenby first, and you will see the back azimuth, and then it hits Ovnat, and you will see the back azimuth. So I will try to run okay, thank you. So now it locks, and then the second one locks. Okay, it was very fast. I would not play it 10 times for you. I think you got the point. The interesting issue is here, is that it took about 3 seconds for the event to arrive here. It takes 0.1 second for us to calculate the back azimuth. Okay, so a little after 3 seconds after the earthquake occur, we can locate it. It's quite robust. And then it means until that wavefront propagates to Jerusalem or to Amman the other way, it still gives us, and then there are different waves, I don't go into details, but it gives you a warning of about 10 seconds before destructive waves arrives in Jerusalem. It was a small earthquake, right? But we are able to provide an alert of a few seconds. I agree, it's not much, but it saves lives. We can go into details afterwards. And the thing is that no other existing system today, mainly because they're based on the network and the need for stations, can provide an alert in these conditions. Okay? So these little array-based algorithms that we have are like building blocks, and they aggregate the data as soon as possible. And they're pretty good for when the source is off the network, and they're very good for all the weird situations where you have a very sparse network. It's everywhere where the conditions are strange or difficult. And it's also good, we're looking now at different projects working for forensic seismicity, like working with the Atomic Energy Commission, or for fracking. That would be a fantastic application. Anyway, now, since our commitment is not only to excel in science, but to the public, we realize that it's great to have a good early warning system, but it's even better if you can try to educate and work on prevention. So together with a Swiss group, we developed this earthquake center. There is actually one now working in southern Switzerland. It educates about 30,000 kids per year and all the civil defense of Switzerland and Italy. And it has two parts. The first one is a series of 30 interactive stations where visitors can learn about earthquake physics, how waves propagate, but mainly how it influences them and their house and their surroundings. And it's very playful and it's interactive. And the second one is also a unique thing, is a big stage, 8 by 8 meters, which replay real earthquakes with all the true parameters, on which people sit for half an hour and feel different earthquakes of all different magnitudes, and learn how to behave under stress. Because most people, even like here, have not been, unlike our president here who was in California during a very strong earthquake, but a lot of people don't know what an earthquake is and certainly wouldn't know what to do. So it's a learning process, and I will just show you very quickly a video about it. So beyond the motion, there is also a lot of sound and visual effects. Okay, and now, just as it was before with the microphones, as soon as people went through it and start relaxing, suddenly you have the secondary effects. And then here you have, because it's in the Alps, there is a dam that broke. It's not a tsunami, but it's basically a flood. You will see coming. And so it really gives you a complete picture of how to behave. And of course, it's adapted to the situation. And also you have slope instabilities. And anyway, I will stop here, and I think we run out of time. I will just conclude by saying that this amazing lab that we have here actually has pushed us to reach out of our standard toolbox in seismology and develop tools, first of all, to characterize the seismicity in the region, but also to move ahead with early warning systems and a lot of other applications. And I think that's the lesson that we get from these life in extreme conditions. Thank you very much.
Thank you very much for a good talk. And I have one question regarding this real-time estimation system. This system assumed the small earthquake, rather small earthquake. If the magnitude 7, whose fault length is about 100 kilometers occurs, do you think this system works? Or?
Look, I'll be extremely careful. We work here with this mini array with an aperture of a few hundred meters and an inter-array spacing between 5 and 12 kilometers. With specific sensors, I will not go into too much detail, but with short period sensors. So with the data I have, I know exactly what I can do. But how it upscales, how we can work with lower frequencies, we need to do it and to work with more things. But I know that within up to 40, 50 kilometers, we're pretty good.
This is because during the last 2011 Tohoku earthquake Japan, the problem of the early warning system was that it predicts the location, but actually the ruptured area is about 300 kilometer region.
Right.
So the point detection is sometimes useless.
Right.
Because the earthquake is 300 kilometers away, but rupture approaching very close to us.
Right. So actually the beauty of it is that since we're independent of all the velocity model, we always point out in the proper direction more. And actually the best is actually to join what you and Japan really is ahead of everybody, and also combine it with mini arrays. So you would have the standard approach plus the mini arrays, so you can benefit from both and gain a little bit of time possibly. Yeah. Thank you.
Okay, thank you very much.
Oui.